Hello folks, let me this is a college algebra course, section zeros of polynomial functions. I'll go over this briefly with multiple examples. So when we say zero of a function, what we mean is the number that makes the function zero. So for the zeros, we simply solve the equation f of x equals 0 to get the zeros of f. So a basic example, consider just a linear function x plus 4, set that equal to 0, x equals -4. So that means this -4 is a 0 of x plus 4. So if it's linear, it's simple. You could just set it equal to 0 and solve it. If it's a quadratic, we have multiple ways to do it. Let me just write one. X squared minus 6x plus 5. So set that equal to 0. You can factor this polynomial. You look for two factors of 5 whose sum is -6. So those are -5 and -1. So we have x minus 5 times x minus 1 equals 0. So we have x equals 5 or x equals 1. So these two are the zeros of the function x squared minus 6x plus 5. Just one addition: for this quadratic function, we call the factors. We call the factors of this function, which is x squared minus 6x plus 5, to be here x minus 5 and x minus 1. These two are what we call the factors. So it's kind of like linear factors. The linear polynomials that divides the actual bigger polynomial. We covered these before, but it's something to mention here. So this was one example. Now what if we have a cubic? We go a little bit further. What if we have a cubic polynomial? I mean, it becomes tricky when you have cubics, but we have certain special ones that we can solve easily. Let's say we're looking for zeros of the cubic: 3x to the third, and then plus 2x squared, and then minus 27x minus 18. So this is a cubic polynomial. We look for zeros of this one. So if you look at the coefficients, you will see that connection. Like there's 3 and 2, and there's -27 and -18. We can take a look at these. So 3 and 2, and the other one is -27 and -18. Can you multiply the first group with a number to get the second group? If you check this, it's easy. You can multiply the first group by -9 to get the second group. So that means factor by grouping works in this case. If you set that equal to 0, you group them 2 by 2. You don't really need to do this test. You can, if you factor them group by within groups of 2, you can clearly see that, because you will be factoring out the like kind of greatest common divisor of those terms, and once you factor that out, you should be coming up with the same kind of polynomial, same kind of linear factor, let's say. So let's see here, for example, it's 3x to the third and 2x squared. I can factor out x squared from both, so I have 3x plus 2, and then here I can factor out -9. I got the same, 3x plus 2. So that means here this factor by grouping works. So we call it factor by grouping, because this time you will take out an x squared and -9. So that becomes x squared minus 9 multiplied by 3x plus 2 equals 0. So we have x squared minus 9 equals 0. X squared equals 9, or x equals minus plus 3. Or you have 3x plus 2 equals 0. So 3x will be negative 2. And then x will be negative 2/3. So we find the zeros. They are minus plus 3, and then that's just negative 3, negative 2/3. So we just studied something like complete factor form. Complete factor form of this polynomial. You write down all the linear factors and the leading coefficient. So leading coefficient is 3. For x plus 3, you have the factor. For x equals 3, you have the factor x minus 3. For negative 3, you have x plus 3. For negative 2/3, you have x plus 2/3. You see, those are corresponding factors, corresponding linear polynomials, which takes that 0, negative 2/3, as a 0. So this is the complete factor form. If you multiply this function, if you multiply these 3 and multiply it by 3, you will get our function f. So this is one type. Let's move into another example. Now, if the factor by grouping doesn't work, now it starts to become a little bit tricky. Let's take, you have f of x given by 2x to the third plus x squared minus 11x minus 10. Now, factor by grouping doesn't work. You can see that if you group them 2 by 2, there's no connection. 2 and 1 and negative 11 and negative 10 with the coefficients. But there's an extra in this problem. So we're given that negative 2 is a 0. So we know that negative 2 is a 0. So folks, this changes the nature of the problem significantly. Now you're going to be able to solve this problem if one of the zeros are given. So negative 2 is a 0 means x plus 2 is a factor of f. So what you do is just divide f by x plus 2. So like you can use synthetic division. So remember synthetic division, I put negative 2, the left corner, which is this is simply this one is the 0 of the divisor, which is x plus 2. And then you write down the coefficients of f for each term, but if there's a missing term, you insert 0. So it's going to be 2, and then 1, and then negative 11, and then negative 10. So I first pull this 2 down, and then multiply 2 by the left top every time and write it in under the next number. 2 times negative 2, negative 4, and I add these. So that makes it a negative 3. Negative 3 times negative 2 is 6. I got negative 5, negative 5, negative 2 is 10. So I got 0. So here is how you read it. We get remainder to be 0, which is what we expected. And then now the f of x becomes, we have x plus 2, the divisor, and here the quotient, folks, will be 2x squared minus 3x minus 5. If I look at this numbers, how we read that in synthetic division. So we got here this one to be 2x squared minus 3x minus 5. See, you know one of the factors, you know the remaining factor, which is going to be a quadratic because this is degree 3. And now you can find simply the zeros of this factor. And how you can do is you can use the AC method, for example, just one AC method. So AC is negative 10. Look for 2 factors of negative 10 whose sum is negative 3. So that's going to be -5, right? And 2. If you add them, you get -3. So let me just write it down. Sum is -3, so that works. So now the next thing you're going to be simply finding the zeros of that polynomial. You divide it into two groups. It's going to be like 2x squared minus 5x plus 2x minus 10 minus 5, that should be 5, equals to 0. See, I just divide this into two groups, just -3. So you can factor out an x from here. It's going to be 2x minus 5. From here you can factor out a 1. So it's 2x minus 5 again. See, the factorization I got will be x plus 1 multiplied by 2x minus 5. So you find the zeros then. So from here we got x equals to -1, or x equals, I mean, you can just saw that it's going to be 2x equals 5, so x equals 5/2. So we find these zeros, see, by using the AC method. So the zeros we find, now we know all the zeros. Those are -2, and then -1, and then 5/2. That's what we get. And then if you want to write down the complete factored form, don't forget you put the leading coefficient 2, then you have x plus 2, then you have x plus 1, then you have x minus 5/2. This is what we get. Now what if the actual 0 is not given? So this is the point now. What if the actual 0 of the polynomial is not given? We are given 1, 0, but now let's say it's not given. So this time, look at this example. We try to find the zeros of x to the third minus 6x squared plus 21x minus 26. Now this time no zero is given. So in this case, folks, what you're going to do is we introduce a new concept. It's just possible zeros, possible rational zeros. This is how we find it. Is this is the factors of the constant term divided by the factors of the leading term. Factors of the leading term, leading coefficient. So in this case, you look at factors of -26. It's negative, minus plus 1, minus plus 2, minus plus 13, and minus plus 26. Divided by factors of the leading coefficient, it's just minus plus 1. So if you look at all the list, it's going to be minus plus 1, minus plus 2, minus plus 13, and minus plus 26. So you see, you're going to be using trial and error to get one of the zeros, but you don't have those many possible ones. For example, if you're trying 3, if you're trying 4, if you're trying 5, you're wasting your time because it's not even in the list. So the ones you try should be on the list. So let's start. Let's look at f of 1. If you look at f of 1, I mean, you plug it in the function. 1 to the third minus 6 times 1 squared plus 21 times 1 minus 26. You see you will get -10. It's not 0. Try another one, f of -1. You will see, use a calculator, that's going to be -54, which is not 0. We want to find a number that makes it 0. Let's try f of 2. F of 2, if you try that one, you will get a 0. So you use a calculator. I mean, really, that's going to be simple, or you can do it by hand. But if you have a calculator, you can use one. So f of 2 is a 0, means that implies x minus 2 is a factor. So x minus 2 is a factor. So now we find one of the zeros. We know it's a factor. We're going to be applying the same technique that we did in the previous problem. So I'll put 2 here and use synthetic division. I have 1, -6, 21, and -26. And I pull this 1 down. 1 times 2 is 2. Got -4. -4 times 2 is -8. That's 13. 13 times 2 is 26. That makes 0. So I get x squared minus 4x plus 13. So that's the quotient. So that means the function f of x is simply x minus 2 multiplied by x squared minus 4x plus 13. Here we go. Another technique. We didn't do it in the previous one, but you can do as well. We did AC method in the previous one. But you can, of course, use the quadratic formula when you're really stuck. For this one, you will see the factoring the actual AC method will not work. You have 13. 2 factors of 13 are just minus, plus 1, minus, 1 and 13 or -1 and -13. Those are the possibilities. So there's no way that you can get -4. So use quadratic formula. A is 1, B is -4, and C is 13. And let's use quadratic formula. So x equals minus b minus plus square root of b squared minus 4ac divided by 2a. So that will give us -4 minus plus square root of -4 squared minus 4 times 1 times 13, and the whole expression divided by 2 times 1. And under the radical, you will get a -36. So it's like 16 minus 52. That will give you -36. So that implies an I. So we got 4 minus plus 6i divided by 2. And if you divide them separately, it's going to be 2 minus plus 3i. See, we got the zeros. You may get complex zeros, which is totally fine. And this is how we write the complete factor form. But let me just write down the zeros first. Those are 2 minus 3i, and then 2 plus 3i. And then the complete factor form will be, we have leading coefficient to be 1, so you don't need to write it down. So it's going to be x minus 2 times x minus 2 minus 3i, and then x minus 2 plus 3i. This is what we have. This looks like a longer problem, the last two, but this is how you find it. So if one of the zeros is given, you factor that term, that factor, like you just divide your polynomial with that corresponding factor of that zero, and then use quadratic formula or AC method if you can factor it. If it's not given, then you have to list the possible rational zeros and then try them one by one, and then whenever one works, then you just move into the synthetic division to get the other factor, and then find the zeros of that corresponding quadratic factor. And I want to say, if this is just the one for the cubic. So is it going to be like this every time for the cubic polynomials? So yeah, I mean, we're assuming that we're going to be getting some sort of like a rational zero at some point. Okay, thanks for watching. Bye.